Section 3.3, it's a very important section, product rule, quotient rule. So we're going to look at a few of the exercises near the end. The first one is extremely interesting, and it's actually at the level of an AP Calculus exam. So in exercise 83, you're given a graph, actually two graphs, function f, function g, and you are told that you have a function p of x that is f of x times g of x, and what is p prime of 1? You also have a function q of x, which is f of x over g of x, and question B asks you what is q prime of 4. So we're going to definitely need these two graphs to answer that pair of questions. Okay, so if p of x equals f of x times g of x, we are given graphs. We might start by thinking, how can I sketch the function p knowing the graphs of f and g? So let's say you want to know the value of p at x equals 0. Well, p of 0 is f of 0 times g of 0, which is 2, 3, 4, 4.5 times 5, which is what? 5 times 4, and 22.5. So the graph of p goes through the point 22.5 up here. What is p of 1? So to find p of 1, I need to find f of 1 and g of 1, which is 4 times 6, 24. Okay, so gradually you could sketch the graph. It's way up here with all these points. But would it really inform you about the slope at 1? Not really. You would just have a list of points and you can't really connect them with like straight lines, so you know it's some kind of curve, but it's not obvious at all what it is. You could also, that's a better idea in fact, try to figure out what is the equation of this line here. We have a segment, it's clearly part of a line. If I could find the equation of this line, picking 2 points, finding the slope, I could also find the equation of that line here. And then if I have f of x for this segment and g of x for that segment, I have some algebra. I can easily multiply these two expressions and it'll give me the equation for p of x. Since this is a line and this is a line, it's ax plus b, cx plus d. If I multiply, I'll find some kind of parabola. My graph for p is some kind of parabola, and I can differentiate. So that might be a second idea we have, and this one is feasible. It's actually a pretty good idea. But there's an even better idea. And the better idea is to remember that we know the product rule. If I know that p of x is f of x times g of x, then the derivative, I can say that this is u times v. So the derivative is going to be u prime v plus u v prime. And that's the best idea. So now that I found the derivative, I can actually calculate p prime of 1 by observing the graphs. This is f prime of 1 times g of 1 plus f of 1 times g prime of 1. If I look at the graph, what is the slope at x equals 1? If I count carefully, I can see that rise over run, it's always 1 over 1, so this is equal to 1. What is g of 1? This is the value of g at x equals 1. It's right here. It's 4. What is f of 1? That's the value of f at x equals 1. It's up here. It's 6. And finally, what is the slope of g at 1? I have to be careful, so I'm just going to take these two endpoints. it's negative 2 over 4, which is negative 1 over 2. So the slope of function p at x equals 1 is 4 minus 3 equals 1. Without even graphing it, I can find the answer. Same process for question B, so this was A, B. If I'm looking for the derivative of q, this is a quotient, so I can use the quotient rule u prime v minus u v prime over v squared. And therefore q prime at 4 is f prime of 4 times g of 4 minus f of 4 times g prime of 4 over g of 4 squared. F prime of 4. So at x equals 4, f prime means the derivative, it's negative 1. G of 4, so the value of g at x equals 4, it looks like it's 3. F of 4, the value of f at x equals 4, it's way up here, it's 7. And what is the slope of g at x equals 4? G is a constant line here, so it's 0. Divided by g of 4 squared. G of 4, I found it earlier, it was 3, so 3 squared. And finally, this means negative 1 times 3 over 3 squared, negative 1/3. A really nice exercise. The next problem we're going to look at is exercise 85. In exercise 85, we have a rectangle. The length of a rectangle is given by 6t plus 5. The height of the rectangle is given by root t. T is in seconds. The dimensions are in centimeters. Find the rate of change of the area with respect to time. So how is the area changing with respect to time? At t equals 0, the length is 0. Oh, sorry. At t equals 0, the length is 5, and the height is 0. So it's not even a rectangle. It's a degenerate rectangle. It has a height of 0 and a length of 5. So the area would be 0. 1 second later, my rectangle has grown. It's 6 plus 5, so the length is now 11. And how high it is? It's high by the square root of 1, so it's 1 unit high. This is my rectangle. And this is the area. 11 times 1 equals 11. And the rectangle is growing. It's growing all the time. It's kind of eating space around it, getting bigger and bigger and bigger. The question asks us, what is the rate of change of the area? So think of it as, how fast is my rectangle eating the area around it? Is it growing super fast, or is it growing slowly, or maybe even is it decreasing in size? To do that, we need to set up an equation for the area. The area is always base times height, so in this case it's 6t plus 5 times root t. I want to rewrite this as 6t plus 5 times t power 1/2, because this allows me to now distribute. This is 6t to the 3 over 2 plus 5t to the 1 over 2. So if I'm looking for the related rate, if you write a prime, usually prime is reserved for d whatever over dx. We usually keep the prime sign for derivatives in terms of x. So when you use a derivative in terms of another variable, you should usually just spell it out. dA over dx that variable. And this time we're looking at how fast the area of the rectangle is changing in terms of t, so dA dt. So the derivative of 6t to the 3 over 2 is 6 times 3 over 2, 18 over 2, 9t to the 1 half, plus 5 times 1 over 2, 5 halves, t to the negative 1 half. And that's it. That's how fast my rectangle is growing. Let's just take an example. At t equals 1, dA dt is 9 times 1, square root of 1 is 1, plus 5 over 2 times 1 over the square root of 1, which is 1. So at this point, my rectangle is growing at a velocity of 23 over 2, which is 11.5 square centimeters per second. What that means is that at this instant, t equals 1, the quickness at which my rectangle is growing is it's growing at a velocity, if you want, it's not right to say velocity, but it can give us an idea of 11.5 square centimeters per second. The important question to understand is, does that tell me that a second later it's going to have exactly 11.5 square centimeters more? The answer is no. Even though this is the instantaneous rate of change of the area, the instantaneous rate of change is always changing. If I tried to find the value at t equals 1.1, it would already be a little bit different. It's exactly the same as if you're in a car and you check the speedometer and you can see that you are driving, or your parent is driving at 60 kilometers per hour. It doesn't mean that an hour later you'll travel 60 kilometers. It would only mean that if you never changed your speed. But what we know is when we drive, we always change our speed. So when your velocity is 60 kilometers per hour right now, it does not mean that an hour later you'll do exactly 60 kilometers, because the rate is changing at all times. All right, that's for the second exercise. Let's move on to the third problem. Here it is. It's exercise 123a. Find a pattern. Consider the function f of x equals g of x times h of x. Use the product rule to generate rules for f double prime, f triple prime, or the fourth derivative. Interesting question. F prime is not even one of the questions. Let me make a decision here. Instead of writing g of x times h of x all the time, I'm just going to write it. I'm just going to use g and h. It's a little concession I'm going to make to proper math, because it's really going to be messy if I have x's all over the place. So f prime is g prime h plus g h prime. Okay, we know that. This wasn't even one of the questions in the exercise, but it's the first derivative. If I want to find the second derivative, I need to look at each one of these terms separately. Firstly, g prime times h. This is a product. That one is a product too. So I need to use the product rule for that. I need to pretend this is u, this is v, and I'm going to do u prime v plus uv prime. So u prime is the derivative of this. It's actually g double prime times v plus u, which is g prime, times v prime, which is the derivative of h. So this is the derivative of g prime h. U prime v plus uv prime. And now I need to do the derivative of gh prime. So this time u is this, v is that. All right, so I'll go quickly. U prime v plus uv prime. v prime is h prime prime. So if we put these things together, we can see that we have g double prime h plus 2g prime h prime plus g h double prime. Shall we try f3? I may want to stop after that because the pattern is the same and it just gets longer. So this time I'm going to have to do the product rule 3 times. For the first one, I have u equals g double prime and v equals h. So u prime v plus u v prime plus, this time I'm going to take u as 2g prime. I'm going to keep 2g prime together, and v as h prime. U prime v plus u v prime. And finally, u prime v plus u v prime. Let's see what we get. G triple prime h. I have one of them. G double prime h prime. I have 3 of them. G prime h double prime, I have 3 of them again. And G h triple prime, I have 1. If we wanted to study the 4th derivative, we could just do u prime v for this term, u prime v for this term, u prime v for this term, u prime v for this term. I'm not going to do it, but if you want, you can do it now because I'm sure you got the idea. What's interesting with this is we notice a pattern. If we compare with the binomials a plus b, this looks a lot like a plus b squared, because a plus b squared is a squared plus 2ab plus b squared. That's a plus b squared. And a plus b cubed, if you know the rule by heart, it's a cubed plus 3a squared b plus 3ab squared plus b cubed. So we get the same coefficients 1, 3, 3, 1. If you don't remember how to get these coefficients, I can quickly remind you that it's the Pascal's triangle. What you do is you always add the 2 numbers above, so 1 and 2 make 3, 2 and 1 make 3, and 1 at the end. This gives us the coefficients 1, 3, 3, 1 that we found here. So that way you can save yourself time. If you want to find the 4th derivative, you can use Pascal's triangle, 1, 4, 6, 4, 1, and you can write the 4th derivative of f. A nice exercise. Finally, exercise 137. Also a nice exercise. It requires a couple of steps, but it's pretty straightforward. That's really the kind of exercises that you need to be able to do. Find the 2nd degree polynomial. They're very nice. They tell us f of x equals ax squared plus bx plus c, but a 2nd degree polynomial, that's what it is. So they wouldn't even need to write this down. You should be able to do it yourself. Such that its graph has a tangent line with slope 10 at the point 2, 7 and an intercept at 1, 0. Since we are looking for 3 unknowns, a, b, c, we really hope that we have 3 conditions. That would be the perfect situation. Do we have 3 conditions? Yes, we do. We know that the parabola goes through the point 2, 7 We know that the parabola has a slope of 10 at the point 27, and we know that the parabola goes through the point 1, 0. So all we need to do is really just set up the equations and then solve the system of equations. So at the point 2, 7, x equals 2, y equals 7, I get the equation 7 equals a times 2 squared, so 4a plus 2b plus c. At the point 1, 0, I know that x equals 1, y equals 0, so 0 equals 1a plus 1b plus c. Finally, at x equals 2, I know that y prime equals 10. This is what it means, that at the point 2, 7, at x equals 2, y prime equals 10. So I need to quickly calculate the derivative. The derivative of ax squared is 2ax, the derivative of bx is b, and the derivative of the constant c is 0. Excellent, I can now plug x equals 2, y prime equals 10 in. 10 equals 2 times a times 2, so 4a plus b. 3 equations, 3 variables. From here, there should be no problem. There's many different ways of solving this. I'm just going to take these two. I'm going to call this equation 1 and this equation 2, like that, using Roman numerals. And I'm just going to calculate 1 minus 2. Just feels like it's a good idea. Shouldn't put an equal sign here. 7 minus 0 is 7 equals 3a, 2b minus b plus b, c minus c, 0. I'm very happy with that. I have no c's left. So now I can basically look at this and that together, and hopefully I can quickly find the value of a. Yes, I can do this equation. Let me call it 3, and let me call this equation 4. I'm going to do 3 minus 4. So 10 minus 7 equals 3. 4a minus 3a equals a. b minus b equals 0. Hooray, I have a. That was very smooth. Now I need to work backwards. How can I find b? Let's just put a equals 3 here. So 7 equals 9 plus b. b equals negative 2. And then if I want to find c, I just need to go back one more level. For example, I can go to this one here, maybe. It looks like it's pretty easy. I have 0 equals 3 minus 2 plus c, and so I find c equals negative 1. So I like to write the function again. F of x equals 3x squared minus 2x minus 1. This is the quadratic equation of the parabola that satisfies the 3 conditions we were asked for. There we go, nice list of exercises.